Okay, so this could be a basis for the identification of nitrogen in a molecule. Let's see here. There's another rule. So you can explain this nitrogen rule here. Uh, Number of unpaired electron. So what about the number of unpaired electron? This is the empirical. This is the table which I would encourage you to remember whenever dealing with this nitrogen rule. You should remember one thing, that if your m by z value is even, if your m by z value is even and your number of unpaired electron is odd, so your number of nitrogen should be even, right? And even if your m by z value is even but your number of unpaired electron is even, then definitely your number of nitrogen should be odd. This is nitrogen rule. And what about the odd m by z value? There are two possibilities. Either you get the even m by z value or you get the odd m by z value. If you get the odd m by z value, it makes two possibilities are there. Either your number of unpaired electron they are odd or they are even. And if your m by z value is odd as well as your number of unpaired electron are odd, it means that your nitrogen number should be odd. So it gives a clue about the whether we get one odd nitrogen or even nitrogen number. So it gives a clue about that number of nitrogen, whether you have nitrogen or not, or how many they are odd, they are even. This information can be gathered from this nitrogen rule just by checking the m by z value. Check if your m by z value is odd and number of unpaired electron is also odd. So it means that odd should be odd. Nitrogen should also be odd. But if your number of unpaired electron are even, m by z is odd, right? Then your uh, nitrogen should also be even. So it's very easy to memorize, I think. Odd, odd m by z. If this is odd, this should also be odd. Odd m by z. If this is even, this should also be even. But what about even? If we get even m by z value, if one is odd, the other should be even. If this is even, this should be odd. This is very simple to memorize, I think. But this gives information about all the nitrogen we have in a molecule because we do not know. We are trying to predict much more informations about our new compound. And one of that key information would be whether they have that molecules has nitrogen or not, or if it has, how many. Here is the number of unpaired. How do you know that it contains the unpaired or the neutral? Whenever a methane molecule is bombarded, you know that it will lose one electron. That's why it would be unpaired. So, what is the m by z value? These are the example of the above things, right? So we let's take this CH4 cationic radical. So the number of electrons are how many? One, which is odd, right? And what about the m by z value? So m by z value even. So it is this table, right? The above one, this one, even. M by z is even. Number of unpaired electrons, they are odd. So we are expecting the nitrogen should also be odd, which is the case, right? It is even because 0 is even number. What about this one? This has no unpaired electron. It means that 0 unpaired electron, which is an even number, right? So what about the m by z? M by z is 15, which is odd. Number of unpaired electron because it does not contain any electron, which is 0, so it is even. So odd, even, and then you are getting odd, even, and you are getting this even. It is this case, even. What about this one? Below one, right? In this, you can see that the number of unpaired electron is 1, which is the case here. What about the m by z value odd? So if odd, this is the odd case. So odd case is this one, right? And how the number of unpaired electrons, they are odd. It is this one, odd. So this should also be odd. It means that the number of nitrogen should also be odd, which is the case here. This is one, which is odd. So it's a very, very good thing to predict the overall number of nitrogens through the nitrogen rule. So this was the nitrogen rule. I think you will understand. This is very easy to thing to understand. Now, moving on, I already explained this fractional about this fractional mass, so I don't want to take much more time about on this. We have already explained the fractional mass, what kind of information they can provide, right? The same thing has been repeated, and this is the same summary page that has been repeated throughout. So what about the neutral losses? What about the common neutral losses? In the mass spectra, we sometimes we see that some of the neutral losses repeatedly. For instance, if one hydrogen is losing, you will get one m minus one peak, right? For if methyl is losing, you will get the m minus 15 peak. Similarly, if ethyl group is losing, you will get m minus 21 peaks. So you can remember all these losses, m minus 15, m minus 21, m minus 31 for the loss of methoxyl radical, right? This one, 29, 31, 43, 45. You can see all these, you should memorize all these, component if we are dealing in the later on when we are discussing the other techniques. This information could be crucial because they gives you information about the neutral losses, right? Loss of water should be minus m minus 18, 28 co, m minus 32, loss of methanol, carbon dioxide. So these are the well-known neutral losses you can study about. Summary page. So move on. Important odd electron ions. So all the this whole phenomena is about odd electron ions because when we are bombarding a molecule, one of the electron that is lost. So that's why we got the odd electron species through the EI techniques. And when that odd electron molecular ion peak, then when reached to the excited state, that later on dissociate and we get the fragment ions, right? Now, okay, this is again repeated. Now, this information is very interesting for you. See that most of the time you are getting the you will be surprised, you will be interesting to know that which of the peak that will gives you the relative maximum relative abundance, right? The maximum intensity. The peak which is most stable gives you the highest intensity, that could be the base peak. So sometimes it's possible that your molecular ion could be a base peak if that is that much stable, which usually in some cases it not happens, but in some cases, in other cases, it's possible that the overall molecular ion peak could be your base peak. Just look at here. This is a compound quinone, sorry, the conjugated compounds, right? Anthracene type. In this case, you can see that there is a conjugation throughout, right? So in this conjugation, this is more stable peak. So if we get the later fragment peaks of that would not be that much stable as much as this one is. That's why the relative abundance of the overall molecular ion peak would be 100%. Similarly, if this we are dealing with this compound, the molecular ion peak would be the base peak because this is highly stable. This one, if you are dealing with this, the relative abundance could be 90%, right? Still it will be the base peak because 90 is the major peak because this is more stable. So sometimes that's why they are saying, but if you are dealing with this kind of ketone, it will be, the relative abundance is this will be around 8. Let me explain in the other video.